Hello students, in this video we want to learn about the concept of Coulomb's law. In the previous videos we have already learnt about the concept of charges, their properties and the various methods of charging. But we have not yet seen how do charges interact with each other. And that is what we want to learn in this video, and that is what is governed by the Coulomb's law. We can also say that Coulomb's law is analogous to Newton's universal law of gravitation. Just like how Newton's law of gravitation tells us about the gravitational force acting between two-point masses, in the exact same manner, Coulomb's law governs the electrostatic force acting between two charges. So let us go ahead and try to understand this in detail, and let us find out what is the electrostatic force that acts between two charges. So here I am going to take 2 point charges. Okay, these are point charges. Just for clarity, we are showing them as bigger particles, bigger spheres. Okay, but they are point charges, their size is negligible. Let's say they have some charge plus Q1 and plus Q2. Now once again, just for developing the theory, for now, I am assuming that both are positive charges. I will tell you what happens if both are negative charges, if one is positive, other is negative, and so on. But for now, let us consider that both of these are positive charges, plus Q1 and plus Q2. And as we can see, they are separated by a certain distance, which we will call as R. Now, as per Coulomb's law, the magnitude of electrostatic force acting between these two particles, the electrostatic interaction or the Coulombic force acting between these two particles will depend on two very important factors. The first factor is of course the charge of each particle, or we can say the product of the charges of the two particles. So we are saying that the Coulombic force or the electrostatic force between these particles, electrostatic force between these two particles, its magnitude Fe depends on two factors. The first factor is the magnitude of both the charges, which can be combined, and we can say the product of the two charges. Once again, I would like you to observe the analogy which I had given, that is with the gravitational force. In gravitational force also we have the force proportional to the product of masses. Same way here, this electrostatic force, its magnitude is directly proportional to the magnitude of the two charges, or we can say the magnitude of the product of the two charges. We are putting mod here because the charges can be positive and negative. So let's say one is positive, one is negative, then the product will be negative. We don't want that negative sign. In gravitation, we do not have to put this mod because masses are always positive. So once again, the magnitude of electrostatic force or the Coulombic force or the interaction between these two charges is directly proportional to the magnitude of the product of the charges. This is the first factor. The second factor also is exactly same as gravitational force, and this is why I'm using the analogy with gravitational force. Here also the electrostatic force, just like gravitational force, follows the inverse square dependency. The electrostatic force is inversely dependent on the square of distance, that is this distance r. Okay, so that is why this distance is important. Whatever is the distance, the force depends on that, and the dependency is inverse square dependency. The magnitude of electrostatic force is inversely proportional to the square of the distance between the two charges. Now, obviously, we can combine these two proportionalities and then write the further relation. So combining these two, I can say that the electrostatic force, the magnitude of electrostatic force is proportional to mod Q1 Q2 divided by R square, right? So this becomes the proportionality relation for the force. And we know if we want to remove this proportionality, then we have to put some constant here. And that constant depends on the medium in which the charges are kept. Now, this is different from gravitational force. In gravitational force, we directly put the constant g here. But in this case, the constant is not fixed. The constant depends on the medium in which the charges are kept. Here, for now, we will restrict our discussion to the charges being kept in vacuum. So I can say for vacuum, this electrostatic force can be further written as K mod Q1 Q2 by R square. All right, where the K value is represented in a special way in this manner. K value is not simply written as K, rather it is written as 1 upon 4 pi epsilon naught. Now I know what you are thinking. Why this complicated expression? Why are we writing it as 1 upon 4 pi epsilon naught? Why not just leave it as K? So I'm sorry to say, but at this point, I won't be able to give you the answer to this question. I know this is the first doubt which comes to the mind. Why are we writing it as 1 upon 4 pi epsilon naught? But you will get the answer as we proceed in this chapter further a little later near the end of the chapter. All right. For now, you will have to take my word here that the proportionality constant K is represented as 1 upon 4 pi epsilon naught. And its value can be found out experimentally, and it is found out to be 9 into 10 to the power 9 in SI units. So in SI units, we will get the value as 9 into 10 to the power 9. But what will be the SI unit? What will be the SI unit of this factor? We can find it out from this formula, right? K is on the RHS. So I can take everything else on LHS and then write the SI unit by using the formula. So for force, the SI unit is Newton. R square, if it goes to the left hand side, then it will become meter square. So let me write this down. This SI unit we are trying to find out. So Newton into meter square, and then we have product of charges which will come in the denominator. So therefore divided by Coulomb square. This is the SI unit. 9 into 10 to the power 9 Newton meter square per Coulomb square. This is the value of this factor K. This epsilon naught is also given a special name. This epsilon naught is what we call as the electric permittivity. The electric permittivity of free space or vacuum. Electric permittivity of free space or vacuum. So free space and vacuum mean the same thing. By free space, we mean there is nothing in that space. It is free from any matter. If there is nothing, if there is no matter, that means there is vacuum. So we can say epsilon naught is the electric permittivity of free space or vacuum, or it is also called as the absolute electric permittivity, because it is for vacuum when there is nothing else, when there is no other medium. We will later see that this parameter, this constant, changes for different materials. If I put these two charges in water, then the result will be different. If I put them in some other liquid, inside some gas, then the result will be different. The force is going to change. We'll come back to that a little later in this video itself. So for now, we are saying this is the force acting on these two charges. There were two charges Q1 and Q2 separated by some distance r. So the magnitude of force acting on the two charges we have determined to be this. And here the value of K is this. 1 upon 4 pi epsilon naught, 9 into 10 power 9 Newton meter square per Coulomb square. This formula we must remember. We can calculate the force between two particles using this formula only. But still, the complete Coulomb's law has not been given. We are talking about force. So there has to be a direction also. We have given the magnitude here. But what about the direction? So we can find the direction of the force acting on these two charges, on these two particles also. And as per Coulomb's law, it is said that the direction of force acting on the two particles will always be along the line joining the two particles or the two charges. Very important. The direction of force. Now we are talking about the direction of force. Okay. The direction of force will always be along the line joining the two particles. And if they are like charges, like in this case, then the force is going to be a repulsive force. So as you can see how I've shown the two forces, these two forces are going to be repulsive forces. If the particles are unlike charges, if the particles have positive and negative charges, then the force is going to be attractive in nature. Okay, so like charges repel each other. Like charges includes positive, positive, as well as negative, negative. Like charges repel each other. Unlike charges attract each other. Very important. And this covers the direction also. All right. So magnitude of the Coulombic force or electrostatic force acting between the two charges, the two particles, is dependent on two factors. First is the product of the two charges, its magnitude, because we don't want the negative sign. Second is the inverse square dependency. It is inversely dependent on the square of separation between the two charges. But combining these two does not give the equation. The formula we get by putting the constant. The constant depends on the medium in which the charges are kept, and this is different from gravitation. In gravitation, we say that capital G is the universal gravitation constant. That word universal is very important. That universal, that word tells us that the value of capital G will be same everywhere. You can take the two particles here on Earth, on Mars, in water, in air, in any medium. The value is going to be the same. Whereas here, if we take the two particles in vacuum, then the constant has this value. If they are taken in some other medium, the value changes. We will talk about it a little later in this video itself. Now this gives the magnitude, but we wanted to find the direction also because we are talking about force. So we are saying that the force acting on both the particles will always be along the line joining the two charges. So that is along this line. In that, two cases can be there. If the charges are like charges, then the force is always repulsive. This includes two cases, positive, positive, and negative, negative. If the charges are unlike charges, then we have positive, negative. The force is attractive. This is similar to how we have the attraction and repulsion in magnets. In gravitation, obviously, I won't be able to make this analogy because in gravitation, we have only positive masses. There is no negative mass. So there is only a charge, only a force of attraction in gravitation. There is no repulsive force. All right. So will these two forces be same or different? Can you think about it? Will these two forces be same or do I need different formula for both? We have just given one formula. For which force is it? For this one or this one? They'll definitely be the same forces because as per Newton's third law, these two forces are action-reaction pair. These are F12 and F21. Okay, here. This is F12 and F21. So because of that, these two forces are going to be equal and opposite forces. They are action-reaction pair. F21 vector is equal to F12 vector. But in opposite direction, so we have to put a minus sign also. So, of course, electrostatic force is also going to follow Newton's laws. And as per Newton's third law, these are equal and opposite forces. So they will be given by their magnitude will be given by the same formula, but directions are going to be opposite. All right. So this is how we describe Coulomb's law. This completes one part of Coulomb's law. Still some things are remaining. We'll continue right from here. In the next part, we want to see how we can write Coulomb's law in vector form directly. Alright, so now that we have learnt about Coulomb's law, what we want to do next is we want to write Coulomb's law in vector form. Now, why are we doing this? Why are we talking about a vector form of Coulomb's law? So the idea is very simple. In the previous case, when we defined Coulomb's law, I gave the magnitude separately and I gave the directions separately. Direction we have to analyze by looking at whether the charges are like charges or unlike charges. Then we have to talk about the line joining the two charges and so on. So many factors are involved and all of them combined are ultimately giving the force acting between the two particles. What we want to do rather is we want to get everything in one place, in one single formula, in one single expression. And that is why we are using Coulomb's law in vector form. Okay, so we will give a single expression which will include the magnitude as well as direction of the force acting on both the charges. So let us see how does this work. So if we are talking about vector form, definitely vectors are going to involve. We'll have to talk about position, force, and so on. So I'm going to consider a coordinate system here. Let's say this is the x and y axes that we have. Z axis can also be there. And this could be in 3D. This whole system can be in 3 dimension. Now we have the two charges, the same two charges, Q1, Q2, plus Q1, plus Q2. We are taking the same case. I'll again tell you what happens if the charges are both negative or one positive, one negative. Now, instead of directly talking about the separation between the charges here, now we will talk in terms of vectors. So I will say that the charges have certain position vectors R1 and R2, right? This is very simple. Q1 is located somewhere at position R1, Q2 is located somewhere at position R2. The analysis is same. We have the same force. We are talking about the same Coulomb's law, same electrostatic force. But now we are talking in terms of vectors. But these are the position vectors of the individual particles. For writing the magnitude of the force, we will need the separation between them. So let me just quickly write the formula that we had got. Fe was equal to K mod Q1 Q2 by R square. So we still need the distance between the two charges, this distance. So I can represent that distance also by a vector. I can say that it is a vector R21. Now I hope you remember your kinematics concepts. What this R21 represents is the position of particle 2 with respect to particle 1. Let me just write that down here. And I'm sure you can recall this from kinematics. This is the position of particle 2 with respect to particle 1. All right. R21, position of 2 with respect to 1, and it is a vector quantity. the magnitude of this vector will correspond to the separation between the two charges. So I can say this R21 vector is nothing but its magnitude is simply equal to this R which we want, which we need. But what exactly is this position of 2 with respect to 1? Can we relate it to these two position vectors? Yes, we can. We know very well by applying triangle law of vector addition, R1 vector plus R21 vector is equal to R2 vector. Let me just write that down. R1 vector plus R21 vector is equal to R2 vector. And therefore, R21 vector is nothing but R2 vector minus R1 vector. And that is what we define as the relative position in kinematics, or relative velocity, relative acceleration. Position of 2 with respect to 1 is nothing but position vector of 2 minus position vector of 1. This is used for velocity also. The same concept, same idea is used for velocity also. Now, if we talk about the forces, then for the like charges, once again, the force is going to be repulsive. The forces are going to be like this. This is F12 vector, this is F21 vector. Force on 1 due to 2, force on 2 due to 1. So I'm saying that the magnitude of this force can be written in terms of this R21 vector. We can write that this F21, okay, let's say we are talking about the force on this charge 2. We want to find this F21 vector. Then the magnitude can be written as K mod Q1 Q2 by R square, where R square is nothing but the mod of R21 square. Okay, the magnitude of force acting on particle 2 due to particle 1 is K mod Q1 Q2 divided by magnitude of R21 square, because we are saying magnitude of R21 is nothing but the separation between the two charges. Now, this includes only the magnitude. We had said we want to involve the direction also. So how do we do that? We can see the diagram and observe from the diagram carefully that we already have a vector in the direction of this force. The F21 vector is simply in the direction of R21, and similarly F12 will come in the direction of R12. What will be R12? Position of 1 with respect to 2. So vector starting from 2 and going towards 1. F12 is going to be in the same direction. So we can say that these two forces are respectively in the direction of the relative position vectors. F21 is in the direction of R21 vector, and therefore for direction I can put the cap and I can say that it is in the direction, it is along the direction R21 cap. So if I want to write this in vector form, finally I can say F21 vector, now I'm not putting the mod, it is equal to K Q1 Q2 by R21 vector mod square into R21 cap. This can be written in one more manner. We know that unit vector is nothing but the vector divided by its own magnitude. So instead of R21 cap, I can write it as, I'm saying this is equal to R21 vector upon magnitude of R21. So if I put this here, if I substitute this relation here, in denominator I'll have one more of this magnitude of R21 term. So I can write this also as K Q1 Q2 by R21 mod cube into R21 vector. Both are exactly the same relations. You can use either of the relations to give the force in vector form. And this is what we wanted to derive. You will also notice one more thing. I hope you have observed it, and that is not a mistake, that is not an error. I have removed the mod from here. When I was writing the magnitude of force, I was again and again putting the mod on Q1, Q2 product. Here I have not put the mod on the product. That is not a mistake, that is not a writing error. In the vector form, we do not put mod on the product of the charges. Try to understand why is that. For like charges, this is what we get, the force along the direction of position vector. If both were negative, then also we'll get the same thing. We'll have minus minus multiplied becoming positive, and the force will still come in the direction of the position vector. So the direction will be the same as the position vector. Either you write it in this form or this form. But if the charges are unlike charges, then what will happen? Just try to see here. If this is positive and this is negative, then the forces are attractive. The forces reverse their direction. But the position vectors will not change. The positions are still R1, R2. Position vectors will still be in the same direction, R21, R12. But the forces will be in opposite direction. The force on 2 due to 1 will be in opposite direction of R21 cap. And that is also getting included in this formula. If I have unlike charges, then one is positive, other is negative, the product is negative, and therefore we'll get minus R21 cap. So it is showing that the force is in opposite direction of the position vector. So all the things are getting included here in this one single expression. And that is the advantage of writing the Coulomb's law in vector form. The magnitude, direction, attraction, repulsion, every concept, every detail is included here itself. All right. So this is how we write Coulomb's law in vector form. I've talked about F21, but I hope you can understand F12 can also be written in a similar way. Just interchange 1, 2 everywhere. Here if I do 1, 2, here also 1, 2, here also 1, 2. So just interchange that 2, 1 with 1, 2 everywhere, and you will have the force on the particle 1 due to particle 2. And as I've already told before, these two forces are going to be equal and opposite forces. All right. So here we complete the second part of Coulomb's law, that is writing the Coulomb's law, the electrostatic force in vector form. We'll continue further, and now I'll come back to the fact that in a medium, the electrostatic force changes between two particles. We had talked about that constant being a certain value for vacuum and changing for other media. We are going to continue the discussion and talk about that aspect. All right, so let us come to the part where we talk about the effect of medium on the electrostatic force. And the parameter involved here is what we call as the dielectric constant. So suppose the same setup which we had initially, that means two charges Q1, Q2 separated by a distance r, is now kept in water instead of vacuum or free space. Or let's say it is kept in some other medium, let's say like glass. Then we are saying that the force between the particles is going to change. The force which we have talked about earlier, the formula or expression which we have given earlier, that works only for vacuum. If the medium changes, then the value or magnitude of the force changes. The direction remains same, but the magnitude changes. And it is found experimentally that in any medium, the force always decreases by a certain factor. And that factor is what we call as the dielectric constant. All right. So let's try to work out and talk about the magnitude of force in medium. So as I said, if the same setup, you can see this is the exact same setup. If it is kept in some medium like water or glass, any medium, then the force changes. We want to find out what this force becomes. All right. So let's talk about the magnitude of force in the medium. And we already know what is the magnitude of force in vacuum. Magnitude of force in vacuum, if I call it as, let's say, FVAC. Okay, I'm going to use the magnitude form, not the vector form, because as I said, the directions remain same. Even in case of medium, the nature is same. Like charges repel, unlike charges attract. But the magnitude changes, so I'm going to focus only on the magnitude. So in vacuum, we have said that the force has a magnitude of 1 upon 4 pi epsilon naught mod of the product of charges divided by the square of distance. All right. So these are the charges. This is the distance between them. So we are saying in a medium, this force is going to reduce by a certain factor, and that factor is what we are calling as the dielectric constant of that particular medium. So let's say it is water or glass, whichever medium it is. In a medium, the force between the charges, so that I'm going to represent by F MED. So that represents medium. It is some other medium. So F in medium is 1 by K times, or I can say it is F vacuum divided by K. Okay. Remember, this is capital K. In some books, this is represented as kappa also. That is the Greek letter. So this is the formula which we get. Okay. When the same setup, same two charges at the same separation are kept in a medium, then the force reduces by a factor K, and this factor K is what we are calling as the dielectric constant of the medium. It will vary from medium to medium. It is not the same for all the media. It will be different for different media. So it is the dielectric constant of medium, whichever medium it is. So let's say if it is water, for water it is found that dielectric constant is approximately 80-81. So the force is going to reduce by a factor of 80. Okay, let's say it is 80. So the same charges, if I keep in vacuum and in water, then the force is going to reduce by a factor of 80. Right? So remember, the force is always reducing. So mathematically, I can say what this means is that for any medium, K is always greater than 1. For any medium, this factor K is greater than 1. All right. Remember, this is capital K. This K is different from the K which I have written earlier in Coulomb's law. K Q1 Q2 by R square. That small k is different. This capital K is completely different. All right. Do not confuse between them. That is why it is preferable to write the constant as 1 upon 4 pi epsilon naught. In fact, this is the technically correct way. We write small k just for convenience. We'll use it several times in solving problems while developing the theory. But the proper way is this 1 upon 4 pi epsilon naught. So as I said, it is always greater than 1, but it will be different for different media. For example, as I said, for water, K is approximately equal to 80. Okay. For air, if we talk about air, then K is slightly greater than 1, just greater than 1. Okay. K is just greater than 1. So for all practical purposes and even for all numerical purposes for problems, we will treat the dielectric constant of air also to be nearly equal to 1, because it is like something 1.00 and then some numbers after the second or third decimal place. So it does not affect that much. The force does not reduce by a significant factor. And that is why we can treat the dielectric constant for air to be nearly equal to 1, and therefore in air, the force will be nearly same as vacuum. So suppose in some question, if they say two charges are kept in air, then do not worry about the dielectric constant. You can assume it to be nearly equal to 1. All right. So this for water and air. For any medium, we have said it is greater than 1. But if we have conductors, if we have metals, then the result is very interesting. If we have the case of conductors, then we say that the dielectric constant of conductors approaches infinity. It is equal to infinity for all theoretical purposes. It is very, very high. It tends to infinity, right? Now, I know you must be wondering, why am I saying this? Why does the dielectric constant become infinity for conductors? And what does this mean? So the consequence of this you can see here mathematically. If K is infinity, then it would mean that inside a conductor, the force, the electrostatic force between two charges will always become 0. So if I take two charges inside copper, the electrostatic force between them is going to be 0. This is very interesting. But I'm afraid I won't be able to tell you the reason at this point. I will give you the reason, but that will come in the next chapter only. So next chapter also we will be continuing with electrostatics, and there we will answer all these things. Why the force reduces in a medium, why for a conductor the dielectric constant is being called to approach infinity. All right. But for now, because in problems you will get this term dielectric constant, you will get different values. For now, for solving problems, you will have to take all this information and use it. The reasoning will be given later. I will justify to you why this happens. All right. Now, there is another approach which is taken for explaining the change in this force when the charges are kept in a medium. Instead of talking about dielectric constant, we say that when we put two charges in a medium, then this parameter changes, the epsilon naught parameter changes. We had said that epsilon naught is the electric permittivity of free space or vacuum. So instead we say that in a medium, the electrostatic force between two particles becomes 1 upon 4 pi epsilon Q1 Q2 by R square. Okay. Observe here, I have not put the epsilon naught. I have not put that circle here. Here we put epsilon naught. Here I am writing only epsilon. So we are saying that this epsilon is the electric permittivity of medium, of that particular medium. Electric permittivity of medium. All right. So just like how we had electric permittivity for vacuum, this is the permittivity of medium. Can you think about, will this epsilon be greater than epsilon naught or less than epsilon naught? It will definitely be greater than epsilon naught, because we are saying that this force is always lesser. In the medium, the force is always lesser as compared to the vacuum case. So therefore, this term in denominator will have to be higher. It will have to be greater than epsilon naught. So we can say always epsilon is greater than epsilon naught. From here, we can also think about the physical significance of this electric permittivity. Okay, what are we trying to say when we say electric permittivity? So this is the characteristic of a medium. This is the characteristic property of a medium which decides how much it permits the electric force to go through it, how much it permits the electric influence to go through it. Okay. So higher the permittivity, lower is the force. That means it does not permit the force to pass through it that much. And that is the importance of electric permittivity. So epsilon will always be greater than epsilon naught, and that is why the force will always be lesser compared to the vacuum case. We can introduce one more term here. This term, the permittivity, if we compare it to density, or let's say refractive index, you've learned about refractive index in 10th class, then we can say, just like how it happens for light, in vacuum it travels the fastest, but in medium the speed of light slows down. Same way here it is happening for electric force. In vacuum it is highest, in medium it reduces by some factor. And just like there in optics, in refraction of light for refractive index, we can define a relative refractive index. Same way here also, I can define a relative electric permittivity. So just like how we do for density, relative density, it is the density with respect to a certain standard substance, that is water at 4 degrees Celsius. Same way I can do here also. So let me remove this part. So we define a term epsilon r, which we call as the relative electric permittivity of medium. Okay. Remember, these terms are for the medium, for a particular medium. This is the electric permittivity of medium. This is the relative electric permittivity of the medium. And we are saying this can be defined in a similar way how we define relative density. That is the density of material with respect to the density of water. Same way here, this is the electric permittivity of medium with respect to the electric permittivity of vacuum. Or we can also write this as epsilon is equal to epsilon naught epsilon r. Now, as soon as I write this relation in this form and substitute it there, if I substitute this relation here, then you will see that this becomes epsilon naught epsilon r. Now, what do you observe? We can clearly see that this part here is the same as the force in vacuum, right? This force in vacuum is the same term that we are seeing here, the remaining part other than epsilon r. So we can say from here that F in medium, the force in medium, is nothing but the force in vacuum divided by epsilon r. So we can also say that the force in medium reduces by a factor of epsilon r, which is the relative permittivity of medium. But wasn't that dielectric constant? The force in medium reduced by a factor of k, where k we called as the dielectric constant of medium. So yes, numerically both are the same things. Numerically, epsilon r and k, they are the same things. Epsilon r is equal to k, the dielectric constant. All right. But why are we taking these two different approaches? What is the meaning of dielectric? Why are we even using this term dielectric? And so on. These will become clear in the next chapter when we talk about dielectrics and their working in more detail. For now, for your understanding, this is all that is important. In vacuum, the force is given by this expression. We write 1 upon 4 pi epsilon naught. In a medium, the force reduces by a factor. The factor by which the force reduces is called the dielectric constant of medium. That factor is always greater than 1. For air, it is nearly equal to 1. For conductors, it is tending to infinity. Instead of dielectric constant, we can take the approach of electric permittivity of medium also. And therefore, this parameter here changes. Instead of epsilon naught, we get epsilon. But then we can relate the epsilon to epsilon naught by introducing relative electric permittivity in this manner. But numerically, both of them are the same things. Epsilon r or k, both are the same things. This is important for you to know because when you solve questions, sometimes they will give dielectric constant, sometimes they'll give the relative electric permittivity. So you must know that both are the same things. They have the same effect on the force. You can see here the effect on force is the same. Here also divided by epsilon r, here divided by k. All right. So this is all that we have in Coulomb's law. This was the third part, and this completes everything related to Coulomb's law. Now we are going to go ahead and take some problems based on all the concepts that we have done till now, and then you can go to the next topic after doing some more practice on this on these concepts. Hello students, in this video we want to take some problems based on properties of charges and Coulomb's law. So we've already studied about these things in the theory videos previous this one, and we want to see what type of questions can be asked based on this. So let us go ahead and see the first question. This is the first question which we have is from NCERT itself, exercise 1.11. A polythene piece rubbed with wool is found to have a negative charge of 3.2 into 10 to the power minus 7 Coulomb. Estimate the number of electrons transferred. Is there a transfer of mass from wool to polythene? So, this question is based on the simple property of quantization of charge. We know that Q is equal to NE, where N has to be an integer. So here, the charge that has been transferred is because of the movement of some number of electrons, and that number of electrons is what we have to find. So that N can be written as Q by E, and we can put the values. Q is 3.2 into 10 to the power minus 7, whereas the value of E approximately can be taken as 1.6 into 10 to the power minus 19. We can cancel this 3.2 and 1.6. 2 will remain, and our answer therefore will become 2 into 10 to the power 12. Okay, 19 minus 7. This minus 19 will go to the numerator and become plus 19. 19 minus 7, 12. And this will be the number of electrons. These are the number of electrons transferred from the piece of polythene to the wool. Now, we are saying, they're asking, is there a transfer of mass from wool to polythene? So if electrons are going from wool to polythene, then of course there will be some transfer of mass, but for all practical purposes and even when we are solving questions in electrostatics, that is negligible. Because just imagine the mass of that piece of wool or the mass of that piece of polythene. It's going to be at least a few grams, or if not grams, then milligrams. Whereas the mass of each electron is very, very small. It is 9.1 into 10 to the power minus 31 kgs. So if you want to know how much mass has been transferred, just multiply these two. You can see that the order of mass will be very, very small. So for all practical purposes, even for solving numericals, this is negligible and we don't have to bother about it. But theoretically, is there a transfer? The answer has to be yes. There is a transfer of mass, right? So this was a simple question. I hope it was clear. Let's take the next question and see what do we have in the next one. This is a board level question. Two bodies A and B carry charges minus 3 microcoulomb and minus 0.44 microcoulomb. How many electrons should be transferred from A to B so that they acquire equal charges? So we have two particles like this, and they have some charges Q1 and Q2, which are given here minus 3 and minus 0.44. Now they are saying that some electrons must be transferred from one to the other, from A to B, and that number of electrons is what we have to find so that the final charges are equal. Now, instead of finding the number of electrons directly, let us try to find what is the charge that should be moved from here to here so that the final is equal. So initially, this one had minus 3
minus 3 mu also I can write. From this, we have to remove some charge so that it becomes equal to the other one. And this other one is going to gain that much same amount of charge. So this is the equation which we get. From 3 mu, some charge was removed. Okay. Or we can simply write it as 3. So this is removed from here and it is gained by the other one. Solve this equation, simple equation, 2q is equal to minus 3 plus 0.44 and that is minus 2.56. Therefore, the charge which has to be moved comes out to be minus 1.28 microcoulomb. This charge is equal to Ne, Q equal to Ne, and therefore N is equal to again Q by E, just like we solved in the previous question. Minus 1.28 into 10 power minus 6. Here we'll have to take minus E, so minus 1.6 into 10 power minus 19. Simple calculation. If we cancel this 1.28, 1.6, so we'll get 0.8 here. So we get the final answer as 0.8 into 10 to the power 13. These many electrons must be transferred. In scientific notation, I can write 8 into 10 to the power 12. These many electrons must be transferred so that the final charge on the particles A and B, on the bodies A and B is equal. All right. So this was the second question. Simple question again based on conservation of charges as well as quantization of charges. All right. Let's go ahead and look at the next question now. All right, so this is the next question. This is from NCERT, exercise 1.2. The electrostatic force on a small sphere of charge 0.4 microcoulomb due to another small sphere of charge minus 0.8 microcoulomb in air is 0.2 newtons. What is the distance between the two spheres? What is the force on the second sphere due to the first? So I'm going to answer this B part first because it's a very simple and direct question. As per Newton's third law, if some force is applied on 2 by 1, then same equal and opposite force will be applied on 1 by 2. So the answer to the B part is simply 0.2 Newton. The same force is going to be applied. For the first part, for the A part, we need to solve. We need to apply Coulomb's law. So we have Fe is equal to K Q1 Q2 by R square, and we take only the magnitude of these charges. So this is a formula which we have, and this is what we have to apply. Now force is given but distance is unknown, so I can rearrange this and write it as R square is equal to K Q1 Q2 upon Fe, the magnitude of electrostatic force. Put the values 9 into 10 to the power 9. Charges are 0.4 microcoulomb, so that is 10 power minus 6 into 0.8. Remember, I'm not taking the sign because there's a mod. 10 power minus 6 upon the electrostatic force, which is 0.2. The 0.2 I can cancel with 0.8 so that it gives me 4. Okay. Now, LHS we have R square. So to solve this, to find R, what we would want to do, what we will try to do is form a perfect square on the right hand side so that taking the square root is easier. So let's do that. R square is equal to 9 is already a perfect square. 10 to the power 9, so that is an odd power. What I can do is write it as 10 to the power 8 and merge one power of 10 with this 0.4 so that it becomes 4. And there is one more 4, and here we have 10 power minus 12, 10 power minus 6 into 10 power minus 6, so 10 power minus 12. So now taking the square root becomes easy. From 9 I get 3, from 4 into 4 I get 4, 10 power 8 will give 10 power 4, and 10 power minus 12 will give 10 power minus 6. So this is 12 into 10 to the power minus 2 meters, which is nothing but 12 centimeters. And this will be the final answer. the separation between the charges is 12 centimeters. All right. So a simple question based on Coulomb's law, but instead of giving the charges and distance and asking us to find the force, they've given the force and asked us to find the separation. All right. So I hope this was clear. And also you should note how I tried to simplify my calculation, because in exams this is very important to save time while solving questions, right? So let's go ahead and take the next question now. All right, so now we want to take some competitive level questions based on Coulomb's law. These will be up to the level of CET and NEET. So let's take the first question and see what do we have. This is a very recent question from NEET 2019. 2-point charges A and B having charges plus Q and minus Q respectively are placed at certain distance apart. Force between them is F. If 25% charge of A is transferred to B, then force between the charges becomes. So there are two charges, A and B. They have equal and opposite charge. So we have plus Q and minus Q. The force between them in this condition is F. Now, what is being done is 25% charge from this is being sent to the other. 25% of Q. So what is 25% of Q? 25 by 100, that is 1/4. So that means from Q, we are subtracting minus Q by 4. Okay. We are subtracting Q by 4, not minus Q by 4, we are subtracting Q by 4. So Q minus Q by 4 will make the new charge as 3Q by 4. And when Q by 4 gets added here, plus Q by 4, then this is also going to become minus 3Q by 4. So of course the charges have changed and the force is also going to change. Initially, this force F, if we write, then it was K QQ by R square. Remember, we take only the magnitudes for calculation of the magnitude of force. For the second part, now if we see, then the new force F dash is going to become K into 3Q by 4 into 3Q by 4 by R square. So we have two extra factors of 3 by 4, 3 by 4, which will become 9 by 16, and KQ square by R square will simply be the original force F. And that is why our answer will be option B, 9F by 16. So the force has reduced, it has become 9 by 16F because the charges have reduced. Whatever was taken from A has been sent to B, right? So you can see it's an easy question, but it was asked recently in NEET 2019. So this type of questions can be asked, even though easy, in competitive exams. All right. So let's go ahead and look at the next question then. Let's see what is there in the next question. All right. So this is from NEET 2017. Again, a very recent question. And you'll see this is a slightly different kind of question. Suppose the charge of a proton and an electron differ slightly. One of them is minus E and other is E plus delta E. So the electron has same charge minus E, but proton has an extra charge delta E. If the net of electrostatic force and gravitational force between the two hydrogen atoms placed at a distance d much greater than atomic size is 0, then delta E is of the order. So we have to find the order of this delta E. The condition given is that the net of gravitational force and electrostatic force is 0. This is the key part. Now, what is going to happen due to this extra charge? So we have two hydrogen atoms. If the charges are not equal and opposite, then of course there is an extra charge. We know that for a hydrogen atom, there is one electron, one proton. So now, because of this change, because of this hypothetical situation, both of these have an extra plus delta E charge. And therefore, even though in nature normally the atoms are neutral, here we have a charged atom. So there is going to be an electrostatic repulsion. and this repulsion, they are saying in the question, is being balanced by the gravitational attraction, making the net force zero. Okay, so this is the electrostatic repulsion, this is the gravitational attraction, they are becoming net zero. F net is zero. Using this, we have to find the order of delta E. So Fe is equal to Fg, K, Q, where each of this Q is nothing but delta E upon R square is equal to G, mass of mass of hydrogen atom into again M, mass of hydrogen atom, by R square. The R square terms get cancelled, so easy. This K I can transpose on the other side so that my calculation is easier. I'm transposing this K here. And now we have to find the order of delta E. So I'm going to put the values, but only the order part so that the calculation is easy. So delta E whole square has an order of G, which is 10 power minus 11, M, which is 10 power minus 27. So we have two such M's, upon K, which has the order of 10 power 9. So this is what we have to simplify. Minus 27 minus 27 minus 54. This 9, if I send to the top, it will become minus 11 minus 9. So minus 20. So delta E whole square is coming off the order of minus 20 minus 54. So that is minus 74. And therefore delta E will come off the order of 10 power minus 37. Option C matches with that, and that will be the correct answer. So you can see a different kind of question. This type of question is a bit unique, but the concept is simple. So don't get scared that, oh my God, such a new situation is given. How will I solve this? How to approach this question? Just apply your basic concepts of physics and you'll be able to solve the question. All right. So all questions may not be always direct. This type of question also you should be able to solve by using the basic fundamentals. Let's go ahead and look at the next question now. All right, so this is the next question. This will be the last question which I want to take in this segment. This is from KCET 2018. So again, a very recent question. Let's see what do we have. The force of repulsion between two identical positive charges when kept with a separation r in air is F. Half the gap between the two charges is filled by a dielectric of dielectric constant force. Find the new force. Then the new force of repulsion between the two charges becomes. So initially we have two identical positive charges, Q, kept at distance r, as F. So F is equal to KQ square by R square. Simple. Now in the next situation, what they are doing is half the separation between them is being filled by a dielectric. So this separation is R by 2. This thickness of the dielectric is R by 2. And it is given that the dielectric constant is 4. K is equal to 4. For such a case, we have to look at the effective distance. And the effective distance when there is a medium is given by root K into the distance covered by the dielectric. And therefore, the F dash new force is going to become KQ square upon R by 2 plus root 4 into R by 2 whole square. Root 4 is nothing but 2. So it will get cancelled with this 2. So we have R by 2 plus R, which will make this F dash equal to KQ square upon 3 by 2R whole square. 3 by 2 is in denominator, so it will actually become 2 by 3 whole square. And we'll have 4 by 9 KQ square by R square. This was nothing but the original force, F, and therefore the final force is becoming 4 by 9 times of that, which is option D, and that will be the correct answer. So this is how we apply the concept of dielectrics. Okay, If this was completely filled by dielectric, then the force directly would become F by 4. But that is not the case. So don't make the mistake of marking this as the answer. There is only a partial dielectric. Only some space is being filled by the dielectric. So I hope all these questions were clear and they help to improve your concepts of the properties of charges and application of Coulomb's law. So I'm going to end it here. You can go ahead and solve some more questions, do the assignments, take the test, and then move ahead and go to the next concept of electric field.